Hello all, welcome to the module. So in this module, I will show you the interfacing of external real world signals to a PC. In order to show, what I will do, I will consider a data acquisition device which is DAQ or NI DAC, USB DAC. I will connect that NI DAC to the PC using an USB cable. Then as we discussed in the last class, I will take LM35, which is a temperature sensor. I will show you the data sheet of a temperature sensor so that you will understand what parameters that we have to look when we are selecting a sensor. Then I will discuss about the internal circuitry of a data acquisition device once again. So I will show you the interfacing connections between the sensor and the data NI USB DAC. Then I will make a small program in the LabVIEW environment where to acquire the data and the parameters that we have to select for acquisition of a data. What I mean by parameters in the sense, how many number of channels that you want to use and what rate at which you want to acquire. Is it a single mode of acquisition or multiple sample acquisition? And using an Express VI, I will show the recording, I will show the acquisition of the signal. Since acquisition will be in terms of an voltages, we have to convert that voltage into a temperature too. So in order to do that, again we require to understand about the sensitivity factor, which we get this information from the data sheet, and from that using the scaling factor or the sensitivity factor, we will multiply the acquired voltage with the sensitivity factor to display the temperature. So this complete procedure, how to do this, how to interface, to which channels we have to interface, everything we will discuss in today's class. So as we discussed in the last class, what about using a temperature sensor. So if you see this is the temperature sensor which is LM35. So the connections to the temperature sensor using RMC cable, I have connected to the terminals of an RMC cable here. So the pin numbers, which is VCC, which is output and which is ground, can be understood from the data sheet. So temperature sensor is LM35. Let me open the data sheet. From the data sheet, we can see that it is a linear and the scale factor, which is nothing but sensitivity. So sensitivity is which gives the relationship between input and output, or in other terms we can say rate of change of output divided by rate of change of input. So the output is in millivolts, whereas the input is a temperature, right? This is a temperature sensor, so input is a temperature. So that's the reason you will see 10 millivolt per degree centigrade, and the accuracy of this sensor is 0.5 degree at 25 degrees centigrade, and the full range is minus 55 to 150. So above which or below which this particular temperature, the property whatever they mention may not satisfy, the scaling factor or the sensitivity factor may not satisfy, and it may not be linear too. So this is the operatable range, above which of course it can withstand for little higher temperature, but it may not meet all the properties they have mentioned, right? And the operating voltage, if you see, it requires a 4 to 30 volts. So any voltage between greater than 4 volts and lesser than 30 volts as an input. Since this is an active sensor, we always have to give an input voltage to operate it, and this is a semiconductor base. So it is required to provide some operating voltage. That operating voltage range is 4 to 30. Then low self heating, which is also another important parameter in case when we are providing higher current. So this causes the internal system to heat or internal IC device to heat, and because of which again the temperature, the accuracy of the measurement will change. So and the nonlinearity is plus or minus 1/4 of the degree, it's a typical, and the output impedance when you see it's a pretty low, so which is 0.1 ohm for 1 milliamps of load. So these are the applications where you can see for what it can be used, and some other information about the temperature sensor, all the information is available, and of course it depends upon where it has to be mounted, because another important thing is the packaging of the device is important, where it has to be mounted, what application that you are using, everything matters. So depends on that application. There are different packages available. So T92, and there body size, the dimensions of it is everything shown here, right. So they have also given the way to connect it. So as I told you, it requires to since it is an active sensor, it required to provide an input voltage, and based upon that, based upon the temperature, it gives an output. So since it is a 3-terminal device, so the connections in order to do everything, it has been provided, right. So these are the different packaging things. So right now whatever I showed you was T092, okay, and there are other packages, TOCAN, SYIC, then we also have LM35DT, this is another package, TO220 package. So right now whatever I showed, the package which is in my hand, T092. Now if you see from the flat and keeping it down, the left side is Vs, the left side is Vs, V out is the center pin and the ground pin is the right side. So here we can see that this red wire connects to this red wire of our RMC cable connects to positive, so positive voltage which can be applied from 4 to 20 volts. Then the center, which is a brown cable, is a V out. Whatever the voltage we can measure is with respect to the ground, and the ground terminal is a black wire. So we have connected in such a way that connecting these wires to any device, to a power source and an oscilloscope or a data acquisition device, will directly connect to the LM35 temperature sensor, right. This is what we have seen from the data sheet. And another important thing what we have to notice is about its sensitivity. As we have already seen previously, how much is the sensitivity? It was 10 millivolts per degree centigrade. And another important thing is output current. When you see the output current, the maximum output current it can produce or it can provide is 10 milliamps, right. So how it is important? When we are interfacing the previous stage to the next stage, if the input impedance of the next stage, the next subsystem is of very high, so that it consumes lesser current from the previous stage. What if the input impedance is smaller? Say if the input impedance is, say the output we are getting is 1 millivolt or 10 millivolt, and the input impedance is of 100 ohms. So now if you calculate it 0.1 10 millivolts divided by 1 ohm or 100 ohms. So if you calculate the current it requires to the current it is required for the next stage should not exceed more than 10 milliamps. If it exceeds, again it drives it takes the energy from the the previous stage, which is the sensor in this case, so that the sensor goes to a loading effect. Sensor cannot drive, right. So this is another important thing which we have to see. And the later on output voltage, the maximum output voltage that you get out of it is -1 to 6, right. It will not give more than that. Then Tj max is 150 degree, it can withstand up to a junction temperature of 150 degree. So as we have already seen about the supply voltage, which is 4 to 30 volts. So accuracy things which we have seen, the nonlinearity things, then the sensor gain, average slope. So this is an average slope again, so with small error. So it will be 9.9 to 10.1. So that's why most of the cases we will consider it as 10 millivolt per degree centigrade. Every 1 degree change in the temperature, it changes the output voltage by 10 millivolts approximately. Now there will be few characteristics or further information about the sensor can be found out from this data sheet, and there will be an application note where you can further refer about the connections of it for better accuracy, and in order to eliminate the noise that creates, like because of the ground loops or common mode noise or differential noises. Here if you see, it is basically a centigrade temperature sensor, which means that it can only measure degree centigrade. In case if you want to show it as foreign heat, you have to use a signal conditioning circuit if you are utilizing the same sensor, or there are other kind of a sensor like LM335 or another kind of sensor where LM75, where it can measure the temperature in degree Fahrenheit. So output voltage will be dependent upon Fahrenheit, or else you have to use a scaling factor which converts the degree centigrade to Fahrenheit to display it in terms of a Fahrenheit. Of course, since we are interfacing it to a microcontroller or a data acquisition device where we are using a software based acquisition hardware acquisition, but converting into a software and displaying it in a software. So in the software we can apply a scaling factor to represent the degree centigrade to a Fahrenheit 2. Now if you see that the output voltage is 0 millivolt plus 10 millivolt per degree centigrade, which indicates that at 0 degree centigrade the output will be 0 millivolts, which means the inherent property of the temperature sensor is it will not give any offset in the output voltage. So if the temperature is 0 degree, the output we get is 0 millivolt. So it starts from 0, no offset at all, no intercept, right. So considering all these factors, now we will see how to interface to a data acquisition. So in order to do the interface, I am using, here we can see NI USB 6008. Since I will be using a LabVIEW software, so this NI software, NI USB devices has a compatibility which has a drivers that can directly interface to LabVIEW. So this is NI USB 6008. It has since it is a data acquisition device, it has onboard instrumentational amplifier as well as an ADC. Further information about that we can see in the data sheet. So here it shows that it has a 12-bit ADC. So yesterday's class we discussed about 8-bit ADC. If we are using NI MIDAC, it has an 8-bit ADC probably. Or if you are using any data acquisition device with 8-bit ADC, whatever we discussed yesterday will work out. Of course, the generalized concept of interfacing, at the same time the selection of ADC is pretty much same, provided the formulas or the number of the resolution of the ADC is slightly changed. So accordingly, based upon the reference that you selected, the number of levels that ADC will have depends upon your the resolution of your ADC. Since in this case it's a 12-bit resolution, so the total number of levels the reference voltage will be divided will be 2 power n minus 1, where n being your where n being the number of bits. So it is 2 power 12 minus 1, right. And another thing is sampling rate, the maximum sampling rate per channel, which is 10 kilo samples per second. So it cannot measure more than 10k samples, 10,000 samples. So as per the Nyquist criteria, as you already aware that what Nyquist criteria says, it says in order to replicate the input signal, the minimum samples required to replicate the input signal is twice that of the frequency of your input signal, So which means that in this case that is the minimum number of samples required to understand the input signal. But to replicate multiple features, in general cases we use 5 to 10 times. Imagine like 5 to 10 times, considering the factor as a 10 times. So which means that 10 kilo samples divided by 10, it can measure up to 1 kilohertz of frequency. If we can use a lower sampling rate, say 5, it can go up to 5 kilohertz as input signal too. And another important thing what we have to see is that whether this particular USB measures a differential or a single ended. What I mean by differential? So in the previous case we have seen two different things. One is, say if I have a resistive divider network where we are measuring with respect to the common ground. So whatever the output voltage we measure here will be with respect to the common ground. So this is called common reference, single ended, because other terminal is directly ground. Whereas if you want to measure, if the requirement is to measure the difference between these two terminals, this particular resistor, say R1, where the other terminal, none of the single terminal is connected to the ground. In this case, such a cases we require to use a differential output, because the voltage at this point, which is with reference to the ground, is different when compared to the voltage at this point with respect to the ground is different. So the difference between these two terminals. That's the reason when we are discussing about a Wheatstone split circuit, we mentioned it as the output voltage is a difference between two resistive divider network configurations. It's a differential output. In case of a Wheatstone split circuit, it is mandatory to use a differential input, whereas in case of a resistive divider, where the output is reference to a common ground, then a single input is enough to acquire the data. So even in the data sheet it is mentioned it's a 12-bit differential and 11 bits single ended. Then maximum input, analog input, AI meaning analog input rate when we are using multiple channels is also 10 kilosamples per second. In case if you require more sampling rate, there is another USB device called 6009. Now the internal circuitry, the block diagram looks in this way. So we have on the sides, if you observe, we have one rail on the right side, one rail on the left side. So the left here, if you see here, it has written with a digital. This guy is a digital terminal, whereas this rail is an analog terminal, right? And we have an USB interface here where we can connect the device, USB DAC device, to the PC using USB cable. As we have seen here, it uses a full speed USB interface to transfer the data from the microcontroller, which is already available inside, to the PC, and it uses an external, it can provide an power supply in case, for example, for active devices like the sensor that we have considered, where it requires 4 to 20 volts or 4 to 30 volts. We don't need to have an external power source to power it. Using the external power supply, where it takes the power from the full speed USB interface, it can provide 5 volts output voltage, and which can support up to 200 milliamps of current. Whereas the interface between the USB to the microcontroller, it's already internally connected. This is an USB microcontroller. The communication between the analog blocks to the USB is using SPI. In between we have 8 channel ADC, 12-bit ADC. So it can support up to 8 channel. As it is a data acquisition device, it should capable to produce an analog output signals too. So in order to do a conversion of a digital signals to analog, so since a microcontroller can only support digital data, so it has a 12-bit DAC internally available. The digital data will be again converted to analog by using this DACs. So even that information can be collected or acquired or given from the analog input terminal blocks. There are dedicated analog input terminals as well as analog output terminals available on the analog rail. So there is something called AO0 and AO01. AO represents analog output channel 0, AO1 represents analog output channel 1, whereas AI represents analog input 0 to 7. So which means a total of 8 channels can be utilized. Along with this, we have also seen about the digital terminal on the other side, in which we can use it as PF10, then PI 0 to 3 and P0 0 to 7, different channels, 0 to 7 1 byte, 0 to 4 another half byte, right? Total of 16 on one side. So the connections to this, as we have already seen, the digital representation of NA USB DAC. So here we have a USB connection. On one side, in this side, 16th to 1 to 16 pins is for analog input, where we have screw terminal connector plug, and 17 to 32 pins, from 17 to 32 we have another screw terminal plug, which is for a digital communication. So the complete pinouts of the screw terminal plugs can be seen here. So one side, the top side is completely for the analog, and which means that here if you see, this particular rail information is seen on the top side here, whereas the other rail, the digital rail information, can be seen on the bottom side. Here if you see, the pin number 1 is a ground, and 2 and 3 is analog input. As I told you, this particular device can support 8 single-ended channel information. It can convert the input voltage using a 12-bit ADC. If you are using a single-ended information as a resistive divided output voltage we have discussed previously, we can utilize all the 8 channels. But if we require to use a differential information, then it supports up to 4 channels. So, plus minus indicates the positive terminal and the negative terminal in case of a differential data. In case if we are using single ended data, the negative terminal can be directly connected to the ground. So, in order to avoid eliminate the noise, to avoid the ground loops, it has been provided with the multiple grounds after each channel, each differential channel, so that directly the terminal pin can be connected to the ground. So, here we can see, and since it also supports for analog output, so we can utilize AO0, which is at 14th pin, right, and 15th pin analog output channel 0 and channel 1, and preceded by a ground terminal 2. In case of utilizing it as a single ended reference data, here we can see the second pin will be acted as analog input 0, whereas a third pin, individual pin, can be considered as analog input 4, right, whereas analog input 1 is 5 and analog input pin number 6 is analog input 5. So, similarly a total of a single ended 8 number of channels can be utilized, whereas a differential input 4 channels can be used. Then similarly for the digital, we also have a different channels, starting from channel 0, 0 to 8, 0 to 7, total of 8 bits, 1 byte, 8 bits, and P10 to P13, so total 4. So, for a counter case, we can use PFI. So, other features of the devices can be seen here. Here it has been also provided with the internal block diagram. Since it uses a single ADC and it can support up to 8 channels, single ended 8 channels and differential of 4 channels, how a single ADC is being interfaced with multiple channels. In order to have an interface, they use a MUX. MUX is a multiplexer. So, here the analog input terminal is connected to this MUX. So, depends upon what channel you select, the MUX will be automatically activated to the channel, and the output of the MUX is connected to PGA. So, PGA indicates programmable gain amplifier. It is a differential PGA, differential programmable gain amplifier, where we can select different gains. Either we can use an external gain amplifier to set the gain, as we discussed yesterday's class, or we can use a software based gain setting, where based upon the gain that we require, the software will select a proper resistor to connect as a feedback to this. So, even that gain can be utilized using a PGA, and the output of the PGA is connected to an ADC. So, in this case the ADC is of 12-bit ADC, analog to digital converter, that is communicated to the microcontroller. So, AI meaning analog input first in first out device. So, here we can see the programmable gain amplifier provide input gains of 1, 2, 4, 5, 8, 10, 16 or 20. So, we have a limited and we can only use the limited gains. In case if we require a gain of 3, this cannot be utilized, we have to externally use a gain. So, when configured for differential measurements, and gain of 1 when configured for single ended measurements. So, both it can be used for differential and single ended. The PGA gain is automatically calculated based on the voltage range selected in the measurement range. Similarly, one thing you should understand about analog input configuration, where otherwise it leads to a noise or errors. Now, in case if we want to measure a differential, so imagine say we have voltage source, where each channel can be referenced to the same ground. We can use a differential amplifier inside, or an instrumentation amplifier inside, where one terminal can be directly connected to the positive terminal, other terminal can be directly connected to the negative terminal. So, whatever the voltage of each terminal is directly referenced to the ground. So, whatever we measure is difference between this particular terminal to this particular terminal, right. So, this is a differential, but whereas we are utilizing the common grounds of the USB device. Suppose say ground reference signal sources, where it has a non-isolated outputs. So, where the signal source is connected to one common ground, where the ground, this common ground will never be connected to that, connected to the USB ground. This is another approach of using it. Then if I was mentioning about a reference to a common ground, where if the negative terminal is directly connected to the ground configuration, which means that whatever we measure is with respect to the common ground. In such a cases, in these cases we can only utilize 4 channels of analog inputs, whereas in such cases we can utilize 8 channels. What is not recommended in utilizing USB DAC configuration, which leads to a ground loops, is by connecting in this configuration, utilizing the grounds of the source as well as the ground connecting to the ground of the USB device can have a grounding loops across this, and it leads to an inaccurate output value, which will also contains some noise into that. So that noise will compromise on the accuracy of the complete measurement. So in this section, what we do, we will use this particular reference to the common ground. We will directly connect the grounds of LM35 to the ground of USB device, so that we can consider it as an RSE, reference single ended. Further more information about the connections and how to take the differential measurements, what different types of sampling rate to be considered, otherwise what happens, what if the input voltage is greater than 10 volts. So how the signal will be represented, complete information can be further looked into that for your own reference. Then similarly for analog output, so since we have already seen that USB 6008 has internal 12-bit DAC, which converts your digital data that receives from microcontroller to an analog output. So using this DAC, it is connected to the analog output channel with a 50 ohms load. 50 ohm load is nothing but your output impedance of your device, that decides how much energy or how much current this DAC can support, right. So the way to connect it is also shown here. If this is one analog output, if this is the load, if it is the load resistance or input impedance of the load is within the limits of output current that USB device can support, we can directly interface output to the ground. Most probably we can use up to 30 milliamps of current, like an LED can be driven, but in case if we want to drive the motors where it requires higher than hundreds of milliamps of current, then this configuration may not be utilized. We may have to design a driver circuit using a triggering circuit, so that the triggering we can utilize the digital outputs of microcontroller and we can trigger on and off, whereas the power required for the load can be utilized from the main source, right. The digital configurations, interfacing of a digital configuration where it can be used as both input and output can be used here. So complete information about how to interface can be seen. So PFI0 is a configurable, that particular pin can be configured as either a digital trigger input or an event counter input. So this terminal can be used as a triggering input or a counter input too. So in case if you want to measure how many number of pulses that it has been achieved, or at this particular triggering input need to activate some other circuit, so this can be used as a proper terminal or as an event counter. So this is about the information about USB DAC. Now we will see how do we create a program in a lab environment in order to acquire the data using USB and the configuration connections between input and output. Here we can see I will use analog input 0 and output will be connected to analog input 0, since the power required for to power the LM35, to power the temperature sensor, can be utilized from the DAQ. What I will do, I will do the connections and I will show you the way that I have connected to it. 31 pin can be used as a 5 volts. The red wire will be connected to the 31. Then all grounds are internally shorted. So any of the ground we can connect it. So I will be connecting it to the 32nd pin. The ground is the black wire. The black wire I am connecting it to 32nd pin. So once I power this device using an USB cable, it produces an output of 5 volts. The 5 volts is enough for LM35 to operate. Now the second pin, which is an output, which gives an output in the range of 10 millivolts per degree centigrade, will be connected to the second terminal. The second terminal here is AI0 plus or AI0. So if we are using as a single reference, as we discussed previously, since the grounds are common in this case, what I do, I will use a single reference. then AI0 I will only connect it to AI0, that is the second pin. So here we can see the red wire is connected to 31, the red wire is connected to the 31, whereas the black wire, which is a ground wire, is connected to the 32nd, 32, pin number 32, and the brown wire, which is output wire, is connected to the second pin. Since I will be configuring the device, second pin. So since I will be configuring the device in a single ended reference mode, I don't need to connect the third pin to the ground. In case if we are using a differential output configuration, then the third terminal should be connected to the fourth terminal to use it as a differential. Since it is single ended, the grounds are common, so whatever the connections we made is good enough. So these are the configuration. So we will see how do we make a program in a LabVIEW software, how to acquire the data in the next class.